this section is about tangent lines. So before we go to this concept, let us review a little bit about slopes, okay, that you have seen before. So let us play with this tool. It is a very useful tool, okay? Suppose we are given a function f of x is x squared, right? We can plot this by giving some specific values of x and compute f of x plotted here in Cartesian coordinate. And this is the graph of this function. It is equal to 0 at 0. And as you can see, the limit of this function when x goes to infinity, where there is a f of x goes. Infinity, right? That is why it's going up to the positive direction in the y direction when x goes to infinity. How about when x goes to negative infinity? It's also go to infinity, right? Very interesting. So now, if we are given a simpler function, g of x is equal to x plus 1, for example, the blue lines here. What is the slope of this blue line? 1. Very good, right? The slope will tell us how stiff the line is. So at x is equal to 1, what is the slope at this point? How about at x is equal to 2? Every point in this line has the same slope, right? But at different points of the function x squared here, they will have different slopes. So for example, here, let us plot it back in our papers. So as we know that come on, what is happening? Sorry. Hey, it's freezing. It kills me. Okay. Oh my God, sorry, just 1 second. Technical. So in Cartesian coordinate, the function f of x is defined as x squared. Then the graph of this is 1, this is 1, negative 1. We'll go through these points. When x is equal to 2, what is y? Yes, thank you. So therefore, it will go through this point and this point here. We connect all these. Then this is the graph of the function f of x. Okay, very good. So at this point, the slope, the tangent line that touch this graph at one point only should be somehow like this, right? And at a different point slope, for example, at 0, what is the slope at 0 here? Yes, it's 0 here. So we see that in general, the slope at each point will change, right? And in this section, we will study how it changed and how we can compute a slope at a point. So if we're given here, we're computing at the point A is equal to 1. So can we find the slope? At the point P, 0, 1, sorry. When x is equal to 1, what is y? 1. Yes, thank you. So this point is our point P right here. P here, right? Good. So in the first section, section 2.1, we have done this before. So the slope at this point, suppose this is the point A. And now if, okay, imagine if the point X is somewhere here, right? So if the point X here approaching 1 from the right-hand side, then this change, we call it delta X, right? And the change in Y is the difference in f of x. Suppose this is the point x0, so that you won't be confused with x in general here. And here is f of 1. And therefore, this guy, we call it the slope, right? M. So M is simply the change in y over the change in x, right? And we study the limits. Then let us write this in a better way. So we call it here MPQ is the slope of the lines P connecting to Q, which will be the change in Y, right, over the change in X. And in this case, if we're given A is this point, then PA would be at P would be this point, and Q, suppose it is in this point. And in general, the function f of x is this curve here, for example. Then the slope at PQ will be f of x minus f of a over x minus a is in the left figure. Is it okay? Yes. Then, now, let us compute. Then this is the slope, or we call it the tangent line. The tangent line, when x come closer and closer to a given point here, the point P, we call this line the tangent line. And the slope of that will be the limit of this when x approaches a, just a definition, okay? Another way to think about this, look at this. When x approaches a, it comes closer and closer, right? And the distance of that, assume that the distance from x minus a here is small h here. Then we can write this limit in another way. The limit, the slope of this will be f of a plus h. It play a role of x here, right? From this formula. And here, and h here is simply x minus a. Just another way to write it. Then go back to our example here. Let us find the tangent line of this parabola before finding this. Okay. Solution for this example. Then, first of all, let us find the tangent line, the slope. Of the tangent line at the point P 1, 1. Okay. According to the definition here, the slope will be m is equal to the limit of f of x minus f of a x over x minus a when x approaches a, right? And in this case, what is a? Thank you, very good. A is equal to 1. Then we replace a by 1, right? It is equivalent to the limit when x approaches 1 of this guy, f of x minus f of 1 over x minus 1. Very good. Yes.
Is A always going to be given to us in the problem?
Yes, A will be different. It depends on your question.
Yeah.
So yeah, it could be any other numbers. And in this specific case, we're given that, okay, we need to compute the slope at this point. That implies A is equal to 1. Okay. Okay. So is it clear why we know A is 1? Then now we're given the formula here, right? This is the graph of the function we need to compute. Therefore, or in other words, this guy is f of x is equal to x squared, right? So we replace f of x by x squared. A is the value. Here, look at this. A is the value at the point we are computing right here, right? In our case, A is equal to the x coordinate of the point we're computing. Is it clear, Colin?
Why is f of x squared?
Oh, it is given here. And yeah, it is given here. Y is equal to f of x, and it is given here. Okay, y is the curve of the function. Yes.
Like, where was A given? Just say A is equal to 1, but what was given in like the problem?
Yes, 1 is given, and it is this point right here. Okay. Is it clear why we're for everyone? Good. Yes. Okay. Then we're given everything. Let us substitute here. It becomes an easier one, right? So then it will be the limit when x approaches 1. What is f of x here? Yes, replace it. What is f of 1? Just 1. Very good. And the denominator, we just rewrite it here, right? Okay. Which formula should we use here? Again, a useful formula, right? A squared minus b squared will be a minus b times a plus b. And in this case, 1 is also 1 squared. They're the same thing. Okay, then we can use the formula. It will be What is it?
X minus 1 plus 1.
Yes, thank you. Oh, nice.
The X minus
Yes, they will cancel each other. Therefore, it becomes x plus 1 over 1, right? I just want to write this step explicitly so that you won't be confused. This term, imagine, it is also x minus 1 times 1. They cancel, then the denominator has just only 1. Therefore, you can definitely write it is a simpler x plus 1, right? Now, this guy is a linear function. Then it is continuous. Therefore, we can substitute the value of this. And what is it? Very good. So we know that the slope of this guy is 2. Okay. Then so they ask us about the tangent line of this guy, right? So if we are given, remember, if you don't remember the formula, the tangent line, the slope of that is 2. It means that if x change 1 unit in this direction, y will change 2 unit. Okay? This is 2, this is 1. And we're given that from this, it means that m is equal to 2. Okay? Suppose this point is what we're computing. Then m is delta x over delta y over delta x, which is f of x minus, in our case, oops, sorry. So we use, I don't remember the name of the line, but equation. It is the point slope form of the equation of the line, okay? Of the equation. That is given is f of x minus f of a is equal to m times x minus a. Very good, thank you. It is actually from this formula, right? Definition of slope, yes.
So did we find the slope to the parabola first? That wasn't the slope of what we just did. Yes.
The slope here, it means the slope at a point of the parabola.
Yeah.
Yeah, and this is the slope. Okay, remember, I should have drawn the function. This is the function, right? X squared. And here is the tangent line. Okay, the blue, the green lines is the tangent line. And we know that we just compute here. M is the slope of the tangent line, which is 2. And A in this case is given, which is 1, right? or in our case, it is f of x minus f of 1 equal to m times x minus 1. Do you agree? This is what we found. And from the previous computation here, we know that m is equal to 2. Therefore, f of x, what is f of 1? Yes, f of 1 is 1. Is equal to 2 times x minus 1, right? Very good. Then can we make it simpler?
We say f(x) squared.
I use a
Oh, no.
I did not use a good notation here. Oh. Let us call the tangent line here is a function g of x here. Won't be confused with with g, the f function. It won't be confused with the function we're given. My bad. Let us call it just simply y. Sorry. Let us write it this way. Sorry. Should we call it y1? Because in the example here, we name y is this parabola. Just don't be confused with that. Okay, just a name, but the meaning is the same. Okay? It doesn't change the meaning. This is how we we remember this formula. Therefore, can we make it simpler?
Just add 1 to the other side.
Very good, thank you, Christian. 2 times x minus 1 and then plus 1 here, right? Or distribute this, we have, yes, and therefore y1 is 2x minus 1, right? This is the tangent line of the given function at the point P11. Now, yeah, we can definitely play with the tools here. Okay. So let us draw the tangent line g of x. We just found that it is 2x minus 1. You see it? The red lines is the graph of x squared. And the green lines here is the graph of the tangent line at a point P11 should be this point. Okay. Is it clear? Very good. Now, we can definitely solve this one using the other formula, right? The other formula using, so we can finish this way, or the method to compute m. M is equal to limit when x approaches a, when f of x minus f of a, or the other formula is f of a plus h minus f of a divided by h, and h, the distance between them, come closer to 0. Okay. And again, we can compute the previous example using this formula. And the function f of x here is, remember, f of x is x squared. So then the limit here becomes what? What is f of a plus h? It's tricky. The function is f of the input. The output will be, it will be a plus h. In our case, now the input is a plus h, right? Then the output should be a plus h and then square, right? Minus, yeah, but let us play with the number a first. A square, right, over h. Is it clear why we have this? Very good. And in this specific case, a is 1, then we replace a by 1, which will be 1 plus h squared. Or let us play with this. We don't have to substitute the value right here. Let us play with abstract things, right? And see, so we'll get used to it. Now, this is something square minus something else square. And yes, a plus h minus a times a plus h plus a, right? Just use the formula. Is it okay? When you use with abstract things, you'll be better. Okay. Now, can we simplify here? Yes, they cancel each other. It becomes yes, very good. Yeah, they cancel each other. Therefore, finally, limit h approaches 0 of 2a plus h, right? A is a constant. H approaches 0, then it will be, yes, just 2a. So we compute this in general A's, right? And this specific case, A is equal to 1, then M at the P, let us call MP, is equal to 2 times 1, and it is 2. The same result as the previous one. Did I say it? Yes.
What is h cancel out?
Good question. Can anybody help me?
Ages. What goes to
So first, we can use the summation law, right, for limit. It will be limit when h approaches 0 of 2a plus the limit of h approaches 0 of h. Then first, the first term is a constant, then the limit of that will be that constant, which is 2a. Limit of h, when h approaches 0, it is the same as limit of x when x approaches 0. Yeah, then it becomes 0. Very good. Let me just write it as okay, is it clear? Okay, very good. So that's it. We'll do the same thing in the test. Computing this result. Are you ready to play with the example in the sample test? Yes. Okay, let me stop this one here.